Hello, everybody, and welcome to the seventh and penultimate webinar in our Train Talks at 12 series on wheel rail friction management. Today, we will be looking in more detail about derailment and how friction management can help to prevent derailments caused predominantly by frictional effects. I'm Jackie Butterfield, and I am the lead applications engineer for LB Foster in Europe. And as before, my colleague Zoe Loveday is here to assist and keep an eye on the chat and field any questions that you might have. Please be aware today I have a really heavy cold, so if I go quietly suddenly, don't worry, I'm just having a coughing fit. So I will try my utmost not to cough, but I can't guarantee. I hope that you've been able to catch our previous webinars in the series, but if you haven't, please don't worry. The recordings of all of the previous 6 webinars are available on the LB Foster website. So today, we'll start again with, as we always do in these webinars, with a quick recap of why it is important to control friction in the wheel rail interface. And then I'll look at the different mechanisms of vehicle derailment, and in particular, those related to frictional effects and frictional forces. I'll then go on to describe the friction management solutions that can be employed to help mitigate against derailment risk, as well as the consumables used. And then I'll just finish up with a reminder of our final forthcoming webinar in the series, which will be next month. So, as always, why do we need to control friction in the wheel rail interface? Without friction, there would obviously be no movement, as there would be no acceleration or braking of the rail vehicles. However, it's very important to control friction at the wheel rail interface, as uncontrolled friction may lead to a number of issues that are listed here. And all of these we've covered in previous webinars. And now, so we're going to look at the last item on the list, which is wheel climb derailment. We'll also be touching on lateral forces as well, which obviously plays a part in some of the mechanisms of vehicle derailment. Just to put it into context, I've just did a quick web search on derailment statistics and found a couple of websites where there are some numbers and statistics on derailments over the past few years. So in North America, this is on the Federal Railroad Administration website. In 2022, there were 952 Class 1 railroad trail derailments. So Class 1 being heavy freight, with around 77% of those occurring in rail yards and 23% on the mainline tracks. Of that 23%, 4 derailments resulted in 4 people being injured and 7 resulted in a hazardous material released to the environment. So that's North America. And then in the UK, here on the right are some statistics on rail vehicle incidents. So the derailments are in green. So you can see the most recent numbers looking back over the last 5 years, with the exception of 2019, 2020, there are around somewhere between 7 and 10 derailments every year. So even though it's a small number, the potential for harm and injury and also hazardous material release to the environment and damage to track and infrastructure are very, very large. And so we need to avoid derailments and minimize the risk as far as possible. So moving on to the mechanisms of derailment. Obviously, here we're not going to talk about derailments which occur as a result of collisions between rail vehicles or infrastructure or road rail plant or equipment. So we're just looking at those that are result of track geometry, quality, or wheel rail interaction. So the simple definition that we're talking about in terms of derailment is that one or more wheels of the vehicle runs off the rails, causing the vehicle to be no longer guided by the rails. There are a number of mechanisms by which this can occur, and these are flange climb derailment, gauge widening and rail rollover, track panel shift, vehicle lateral instability, and others such as wheel flats and wheel defects, which cause the vehicle to derail. So on to the first mechanism. Flange climb derailments generally occur where the wheel experiences a high lateral force in combination with a reduction in the vertical force. So effectively the vehicle, the wheel is lifting off the rail in the presence of a high lateral force. This tends to be induced by a large wheel set angle of attack in curves, and the vertical force can be reduced where you have poor vertical load equalization, for example, on rough track, if you have a large track twist, or if the car is the carriage is experiencing roll resonances. This tends to occur predominantly in curves, but can occur at other track features and geometries, such as switches and crossings. So hence, going back to the statistics in North America, where the majority of the derailments were in yards and depots, these are the areas where you tend to have a lot of switches and crossings and special track geometry. So the base level of lateral force that you would experience in a curve will depend on the curve radius. It will also depend on the wheel and rail profiles and the relative wheel and rail profiles as well. So how conforming are the wheel and rail profiles to each other? It will also depend on the vehicle itself, on the bogie suspension characteristics. So it's very much a function of dynamics and also a function of vehicle speed. So these factors combine to generate a base wheel set angle of attack, which in turn generates the base level of lateral curving force. A significantly misaligned bogie is likely to induce a higher wheel set angle of attack, and any track irregularities and dynamic discontinuities may lead to an additional increase in the wheel lateral force over vertical force ratio, which I'll call L over V from now on. So when this ratio exceeds the limit that the wheel can sustain, the flange climb occurs. So wheel climb derailments can also occur on tangent track, where you have track irregularities and the dynamic motion is severe, such as during vehicle hunting and aggressive braking. So the sequence of events leading to wheel climb is shown in the images at the bottom of the screen. So in the first image, the vehicle is in tangent track, so you have a normal contact patch in the center of the wheel tread. The vehicle then moves into the curve in B, and you start to have lateral movement, and which leads to flanging contact with the gauge face of the rail. The flange contact angle increases, and then the lateral creep, which is a resultant of this, assists the wheel to climb the gauge face, eventually resulting in picture E, where the wheel has left the rail completely. So that's the sequence of events. So there have been various ways of quantifying the risk of derailment based on the wheel rail dynamics. And some of these are purely based on a resolution of the lateral and vertical forces in the wheel rail interface, but also some take into consideration of the time the wheel flange and gauge face are in contact, and some look at the length of contact in the wheel rail interface. So these are the Nadal single wheel, L over V limit, the Weinstock or Weinstock axle sum, L over V limit, and then there are others which are being developed by specific railroads that are looking at distance limits, time duration, and wheel climb distance. So We don't have time to go into any detail about all of these today, so I'm just going to look at the first two, which are the most commonly used, which is the Nadal single wheel L/V limit and the Weinstock criteria. So Nadal's criteria. So the original work by Nadal goes all the way back to 1908. And he theorized that the wheel material at the flange contact point is moving downwards relative to the rail material due to the wheel rolling around the tread contact. And wheel climb occurs when that downward motion ceases with the friction saturated at the contact point. So based on his assumptions and an equilibrium of the forces at that single point of flange contact, which is indicated by where the L, the V and the F3 meet, the ratio of L/V is the tangent of the flange angle, delta, minus the coefficient of friction, divided by 1 plus the coefficient of friction multiplied by the tangent of the flange angle. So if the maximum contact angle is used, this gives a minimum wheel L/V ratio at which the wheel climb derailment can occur at a given contact angle and coefficient of friction. The higher the contact angle, the higher the L/V ratio needs to be to control derailment. The limit to Nadal's work is that he only considered one wheel. So he doesn't take into consideration the friction effect of the non-flanging wheel as well. So put graphically, this shows the relationship between the coefficient of friction, so the coefficient of friction are the curved lines, and the Nadal's L/V limit and the contact angle. So you can see the higher the friction, the lower the limiting value at which derailment will occur. So this is obviously where friction management comes in terms of reducing that friction. We reduce the risk of derailment because the L/V ratio is higher. Following on from Nadal's work, in 1984, Weinstock proposed a much less conservative but more accurate wheel flange climb criterion. And this sums the absolute values of L/V on the two wheels on the same axle. So the L/V ratio on the flanging wheel is evaluated using Nadal's equation, and on the non-flanging wheel, it's generally represented by the friction coefficient of the wheel-rail interface. This Weinstock value can actually be evaluated practically using an instrumented wheel set that can measure the L/V on both wheels. So then the sum of those gives you the Weinstock limit. The criteria is seen as being more accurate and less sensitive to errors or variations in the coefficient of friction. So the graph on the right shows a comparison between the Nadal values and the Weinstock values for a constant flange angle of 68 degrees. So you can see the Weinstock is much less conservative, and so you can get away with a much higher L/V ratio with Weinstock than you can with Nadal. So moving on to the second mechanism of vehicle derailment. This is gauge widening and rail rollover. So derailments can occur with wide gauges and lateral rail deflections known as rail rollover. So high lateral forces generate track spreading forces, which then leads to lateral movement or roll of the rails, which is shown in the images on the right. So a high angle of attack on the leading axle will lead to high lateral forces. The top figure shows the flanging wheel rolling over, which leads to the non-flanging wheel dropping between the rails. And alternatively, the bottom shows the gauge widening as a result of the lateral forces. And then the non-flanging wheel again drops between the wheels. Similar criteria to evaluate the risk of derailment have been developed for this type. It's also been found that tread hollowing can increase the risk of this type of derailment. The next method is track panel shift. So where rail rollover and gauge widening was simply a movement of the rails, this is an actual movement of the whole track panel, so sleepers and everything. And so not just the widening of the gauge. And this movement is caused by repeated axle loading and high lateral forces. And this tends to happen on tracks that have a low resistance to lateral forces. So this could be due to poor track quality or ballast quality, or even a soft track substructure. This also tends to get worse or more prevalent with increasing speed and vehicle load. Again, risk criteria have been developed to try and predict and limit the risk of derailment. The next one is vehicle lateral instability. So derailment can also occur with poor lateral stability, i.e. vehicle hunting. So wheel sets will naturally oscillate around the centre line of the track as shown in the figure. But if the conditions are extreme, this can lead to extreme lateral movements and oscillations, and therefore to high lateral forces, which can lead to the derailment. And then the final one is wheel flats and defects. So wheel slide due to low adhesion may lead to the formation of wheel flats. If the wheel flat is severe enough, it may lead to a derailment. And this is what occurred at Petrel Bridge in Cumbria in October 2022. So a low adhesion event led to a wheel slide and a wheel flat on just one particular axle. So you can see the actual picture of the wheel flat on the top right image. So in this derailment, 5 freight wagons were derailed and there was significant damage to the track and to the bridge itself. Fortunately, there were no injuries. If you would like to read more, the accident report is available on the RAIB website, so the Rail Accident Investigation Board. So what can we do to try and prevent and lower the risk of derailment? So as we've seen in the previous slides, the various mechanisms of derailment, friction plays a significant part in causing the derailment, whether that's by increasing the lateral forces or by the coefficient of friction between the wheel flange and the wheel. And so friction management can certainly help to mitigate against that risk. So one option is trackside gauge face lubrication. So here we are reducing the coefficient of friction between the wheel flange and the rail gauge face, and therefore reducing the risk of wheel climb derailment. So you're reducing the coefficient of friction on the top and the bottom of that criteria. So this can be achieved either by using a hydraulically actuated unit shown in the bottom right, or by using an electrical gauge face unit. It's also worth noting that lubrication of check or restraining rail can also help in terms of reducing the risk of derailment. Obviously, if you have a check or a restraining rail and you have back of flange contact there, and there is a high coefficient of friction between the back of the flange and the restraining rail, then that will also increase the risk of derailment and wheel climb. So the other option is to use a trackside top of rail friction modifier unit. So here we're reducing the coefficient of friction between the wheel tread and the rail head. And this reduces the lateral forces in curving. So you're reducing the lateral forces, you're reducing the angle of attack, and you're reducing the track spreading forces. It also can improve the vehicle steering and reduces hunting. So in terms of applying from a trackside unit, this is predominantly only done via an electrical powered unit. Another option is to actually adopt an onboard friction management solution. So you may want to lubricate the wheel flanges directly by using a flange solid stick system, or use a tread stick system, which will control the coefficient of friction between at an intermediate level, typically between 0.3 and 0.4. And again, by reducing the coefficient of friction on the flange, you're reducing that risk of wheel climb derailment. And likewise, by using a friction modifier, you're reducing the lateral forces in curving. And then the final option, which ties only really into that final mechanism of derailment in terms of the wheel slide, we're looking at a traction gel applicator. So the traction gel applicator, or TGA, is a trackside unit which is used to apply a traction gel in high risk or critical areas where you know that you have a high incidence or risk of low adhesion. So you're reducing railhead and wheel tread contamination, and therefore you're restoring the coefficient of friction to dry levels and reducing the risk of generating a wheel flat. So this obviously needs to be placed carefully, and because the wheel slide and the flats may occur a significant distance away from where the derailment occurs. And this was the case with Petrel Bridge. The original low adhesion event was several kilometres away from the actual derailment. And so you need to carefully decide where you need to place these units based on history of low adhesion incidents in that particular area. So just in summary, this is a table just showing those mechanisms of derailment that we've talked through, what the potential friction management solution could be, and what the overall effect is. So obviously for flange climb derailment, you have gauge face lubrication, wheel flange lubrication, or top of rail friction modification. And they are all reducing the friction between the wheel and the rail, reducing lateral forces and the angle of attack. And likewise with gauge widening and rail rollover, top of rail friction modification or wheel tread sticks can help with that mechanism. Track panel shift, friction modification again can help in reducing the lateral forces, as with vehicle lateral instability. And obviously low adhesion wheel flats, you're looking at traction enhancers. Friction management is just one of the tools that you can use to help reduce the risk of derailment. Obviously, all of your other wheel rail management capabilities need to be taken into consideration in terms of controlling the quality of the track bed, the maintenance, the wheel and rail profiles through grinding and wheel turning and all those things. So friction management is no way a magic bullet, but it can certainly help to de-risk derailment. So in terms of consumables that you would use, for gauge face lubrication, you would use a grease. For top of rail friction modification, you would use a friction modifier such as L.B. Foster's Keltrack. For the wheel flange, you could use solid sticks, or there are alternative oil spray systems available on the market. L.B. Foster does have a liquid LCF product that we market, which tends to be used in depots, which can be painted directly onto the wheels once they come off the wheel lathe. So what tends to happen in depots is once the wheels have been turned back to their profile, the wheel surface is very, very rough. So as the wheels come out of the depot and they hit all of those switches and crossings coming out of the depot, there is a much greater risk of wheel climb derailment. And so by painting on this liquid LCF after the wheel turning, you're just reducing that risk until the wheels are back to their kind of normal roughness in their normal kind of operating state. And then the final consumable is traction gel, and LB Foster's is Alleviate. So in conclusion, there are multiple mechanisms for wheel and vehicle derailment. Friction influences the majority of these mechanisms that we've talked about today, and therefore friction management solutions can be deployed to mitigate against derailment risk. So just finally, our last Train Talks at 12 is going to be on Wednesday, the 9th of April. And here I'm going to be talking about how do you measure whether your friction management is working and giving you the benefits that you need it to. So we're going to be talking about validation and trials, and also a bit about best practice as well. So I hope you can join us for that webinar. So really all that remains is for me to thank you for attending today. And if you have any questions, please pop them in the chat and I will hopefully be able to answer them for you before my voice gives up altogether. Does anybody have any questions? You're very welcome, John. Thank you, Simon. Well, if nobody has any questions, if you think of anything after the event, please get in touch. And I'd be happy to answer any questions that you might have. Okay, I hope to see you next month.